Today's lesson is all about the discovery of nuclear fission. The goal is to understand the process of nuclear fission. So as you read in the book, nuclear fission was discovered somewhat by accident by two scientists named Fritz Strassmann and Otto Hahn. And they had been testing a sample of uranium and were very, very surprised to find that after they were bombarding uranium with neutrons, they discovered barium. So they didn't know what to make of this. So they reached out to a third scientist named Lise Meitner, who had worked quite a lot with Otto Hahn, to ask for her opinion. And her opinion, her perception was that they had actually split uranium into two separate elements. And this was the first time anyone had done this, and this is called fission. So here are two diagrams that you saw in the book that I think do a good job of explaining the basics of nuclear fission. What happens is that a neutron hits the nucleus of an atom. So fission doesn't happen spontaneously. Fission happens when a neutron goes flying into the nucleus of an atom. The neutron sort of adds itself to the nucleus, making it very unstable. And what the nucleus then does is it splits in two. And you can see that in this diagram over here, where uranium is the parent. Uranium is bombarded with neutrons, and then it actually breaks into two much smaller elements. It's going to break into barium and krypton. And as you can see in the caption here, when this happens, the uranium disappears because it's no longer uranium. It's become two whole new elements. So I've included here two more diagrams that illustrate the exact same process. There's no difference other than they're just a different visual representation. So in this first diagram, again, you have nuclear fission of uranium. So you have uranium-235. So that's the isotope that we used for nuclear fission of uranium. A neutron hits that uranium, and you can sort of see here that when the neutron hits the uranium, it goes up in mass because it has one more particle. So it's now uranium-236, and it's unstable. And so that unstable uranium isotope is going to break down into two smaller elements, krypton and barium. And you'll notice that when that happens, three more neutrons are generated. And that's going to become important later in the week when we talk about something called the chain reaction. In this diagram, you have the same idea. You've got a neutron. The neutron's going to bombard uranium-235. And when that happens, krypton and barium are formed, as well as three more neutrons are released. And what I like about this diagram is it clearly shows that there is a massive amount of energy released in that process. And that's one of the things that makes nuclear reactions so unique and so relevant to bomb development in World War II, is that they realize that when you split an atom, you're going to release an incredible amount of energy. And that's because of the energy that's binding the nucleus together to begin with. So in order to understand why so much energy is generated, we need to talk about one more concept related to the nucleus, and that's called the strong force. So again, here I've taken a diagram from the book, which you saw in today's reading. So we've got two protons. Now you've learned in chemistry that opposite charges repel, and that's because of a force called the electrostatic force. And so according to the electrostatic force, two positive charges, any similar charges, are going to repel from each other. And so these two protons, you can see that in the big blue arrows in the background, are going to want to repel. Now, if you think about a nucleus, though, inside a nucleus there are piles and piles and piles and piles of protons crammed together. So how can we have so many protons crammed together in the nucleus if they're all repelling from each other? And the answer is a second force called the strong force. And the strong force is exactly what it sounds like. It's a very, very, very strong force that locks the nucleus together. And you've got a nice little sort of illustration of that to the right over here. You can see the elastic band tying the nucleus together and the word strong. So the strong force is just a force of nature that keeps the nucleus bound together, but it has to be incredibly, incredibly strong if it's going to counter the electrostatic force that wants all of those protons to separate from each other. And so the reason that a nuclear reaction is going to produce so much energy is that we're basically unleashing the energy of the strong force. The strong force is what keeps the nucleus bound together. So when we split an atom, we're splitting the nucleus in half, we unleash the energy of the strong force. And you guys have probably all seen Albert Einstein's famous equation E equals mc squared. That equation is actually a way of predicting the amount of energy, E stands for energy, that will be released when we split an atom and unleash the power of the strong force. And so in review, we talked about Lise Meitner, Fritz Strassmann, and Otto Hahn, the scientists who are really responsible for the discovery of fission. We talked about how fission begins when a neutron hits the nucleus of an atom, in this case uranium, making it unstable. And when you have that unstable uranium atom, it's going to split. When it splits, it creates krypton and barium. It also releases 3 neutrons and a huge amount of energy. And that huge amount of energy comes from us unleashing the strong force, which is the force that binds the nucleus